Let's embark on a journey to understand Galois theory. This theory explores the hidden symmetry in polynomial equations. In particular, we will understand why some equations cannot be solved by radicals, that is, by using square roots, cube roots, and so on. The fundamental problem that Galois theory addresses is, can every polynomial equation be solved using only arithmetic operations, that is, addition, subtraction, multiplication, division, and radicals? For example, consider the equation x to the power 5 minus 6x plus 3 equals 0. Galois theory helps us understand why no radical solution exists for this particular equation. Symmetry is the key insight that drives Galois theory. Consider a simple equilateral triangle. It has 3 rotational symmetries and 3 reflection symmetries, making a total of 6 symmetries. Similarly, polynomial equations possess hidden symmetries among their roots, and understanding these symmetries is crucial to determining whether the equation can be solved by radicals. The Galois group captures all possible ways to permute the roots of a polynomial, while preserving algebraic relationships. For example, consider the simple polynomial x squared minus 2 equals 0. The roots are square root of 2 and minus square root of 2. The Galois group in this case consists of the identity operation, which leaves the roots unchanged, and a swap operation, which interchanges the 2 roots. This group is isomorphic to Z2, the cyclic group of order 2. Field extensions involve creating new number systems by adding roots to existing fields. Imagine an extension tower. We start with the field of rational numbers denoted by Q. By adding the square root of 2, we create a larger field denoted by Q of square root of 2. Further, by adding the square root of 3, we extend the field to Q of square root of 2, square root of 3. This process of adding roots creates larger fields that contain the original numbers and the newly added roots. The Galois correspondence is the fundamental theorem that reveals a perfect correspondence between field extensions and group structures. It establishes a bridge between fields and groups. On the field side, we have subfields, extensions, and degrees. On the group side, we have subgroups, quotients, and orders. The Galois correspondence links these two seemingly different mathematical structures, providing deep insights into the solvability of polynomial equations. The connection between the solvability of an equation by radicals and its Galois group is a crucial insight of Galois theory. An equation is solvable by radicals if and only if its Galois group is solvable. A group is considered solvable if it can be broken down into a series of abelian quotient groups. That is, we have a series of subgroups G equals G subscript 0, contains G subscript 1, contains and so on, contains G subscript n equals the identity element E such that each quotient group G subscript I divided by G subscript I plus 1 is abelian. Let's consider some classic examples. For quadratic equations of the form x squared plus bx plus c equals 0, the Galois group is S subscript 2, which is isomorphic to Z subscript 2. The order of this group is 2, and it is solvable by radicals. For cubic equations of the form x cubed plus bx squared plus cx plus d equals 0, the Galois group is S subscript 3, and its order is 6. This equation is also solvable by radicals. Now let's turn our attention to the Quintic problem, that is, degree 5 equations of the form x to the power 5 plus bx to the power 4 plus cx cubed plus dx squared plus x plus f equals 0. The Galois group for the general quintic equation is S subscript 5, and its order is 120. However, unlike quadratic and cubic equations, the general quintic equation is not solvable by radicals. This is because S subscript 5 is not a solvable group, as it contains non-abelian simple subgroups that cannot be broken down. The Abel-Ruffini theorem states that there is no general algebraic solution to polynomial equations of degree 5 or higher. This theorem was first proved by Paolo Ruffini in 1799, and later by Niels Henrik Abel in 1824. The key implications of this theorem are that there is no universal formula like the quadratic formula for solving quintic and higher degree equations. Some specific equations can still be solved by radicals, but a general solution does not exist. Consequently, numerical methods often become necessary to approximate the solutions. Galois theory finds modern applications in various fields, including cryptography, coding theory, number theory, and physics. Galois theory has had a lasting impact by revolutionizing mathematics and revealing the deep connections between algebra and symmetry. Here are some key takeaways from our exploration of Galois theory. Symmetry determines solvability. Groups and fields are deeply connected. Some problems have inherent limitations. Abstract algebra has practical applications. Galois theory shows how impossibility can be as profound as possibility. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.